We're starting. We have it. Let me see. We're gonna start in a few moments. So welcome everyone to today's seminar. Today we have Dr. Leonard Burtschner, who's obtained his PhD in 2011 at the Max Planck Institute for Astronomy in Heidelberg, and worked as a postdoc at the Max Planck Institute for Extraterrestrial Physics on the VLTI instrument Gravity in Garkey. From 2017 to 2022, he was a staff scientist at Leiden Observatory in the Netherlands and worked for the ELT instrument METIS as a calibration scientist. He currently works as a climate and energy policy advisor at the Munich-based NGO. You can pronounce that later, I can't. Leo is also a co-founder of the grassroots network Astronomers for Planet Earth, and currently serves as a member of the board of the A4E charity, recently registered in Germany. He has also initiated several international activities to help combat human-induced climate change through an astronomical perspective. So thank you so much, Leo, for
Are you still there? I can't see your video anymore. Oh, someone else has taken over screen sharing. Is that the intention? Should I claim the screen back?
Yes, please. I think Anna's connection is down, but
Oh, okay, that's too bad.
let's see if she rejoins.
Connection at the moment. Let's see.
But do take the screen back if you can.
Okay, then I do take the screen back. But let's see if Anna's coming. Like I see Santiago as host. Is that
Santiago is Basilio?
Yeah, is he in the seminar room or?
I don't think so.
Okay. Just
Onde é que é o microfone? Onde é que ele fica? Aqui?
a câmera também morreu.
A câmera morreu.
Parece que o Bica está compartilhando a tela dele.
Importante avisar pelo chat, estamos com esse problema, né? Para que não fique,
I think they're back.
fiquem totalmente perdidas. Né? Então avisa
Basilio
pelo
is
chat, for having audio
coordinated.
problems,
Yeah.
stand by. Hello, can you hear us?
Yes.
Oh,
Okay.
great. I don't know what happened. Cable disconnected.
Can happen.
Okay, while I was introducing you. So we're restarting it.
No worries. Okay, should I start?
Please.
Just a second. I think there's something funny here. Yeah. Share your screen again, please.
My screen should be shared, but I see that two people are currently screen sharing. Eduardo Bica, who's online, is also sharing the screen.
Let's kill Eduardo Bica's screen. I don't know how to do that.
Okay, looks like now have the right screen.
Yeah, I put Vika in the waiting room. How do I put him back? Okay, you can start, Leo.
Okay, do let me know if there's any other issue,
Okay.
and then we'll see. All right, well, thank you, Anna, for the introduction, and thank you for the invitation and for having me virtually in Porto Alegre to talk about Astronomers for Planet Earth. And the big question, is there a planet B? Obviously. So yeah, my name is Leo Burtschner. I would still describe myself as an astronomer, having worked in the field for 15 years, although at the moment my astronomy work is mostly based on outreach, and my actual professional work is on climate policy. As you may know, this actually comes quite timely. Tomorrow, the COP28, the International Climate Conference, starts in Abu Dhabi. Very much criticized for various reasons. We can go into that later. But yeah, this, of course, is an extremely pressing topic, not just today, but any day. All right, so this talk has essentially 4 parts. I would like to give an astronomical overview. I understand that the audience is mixed between professional astronomers, students of astronomy, but also other scientists and students. So I will try to be both specific, but also broad to cover all needs. Then I have a little section on the question whether Earth is special. And then we ask the question what astronomers can do to protect this possibly special planet that we happen to live on. And in the end, I want to present to you the group Astronomers for Planet Earth that a couple of astronomers founded now more than 3 years ago. And I would say the organization is thriving with now more than 2,000 members and a legal charity organization registered recently and first funding coming in. So we're growing, and hopefully you will be hearing more from us in the coming years. All right, so where are we? Well, we are here on Earth in the outskirts of a galaxy called the Milky Way that you in the southern hemisphere have a much better view on than I in the northern hemisphere here, because you happen to look into the center and I look mostly outside to the center. So I hope you do enjoy the view when you have it at the night. And this view gives you, obviously, you will see lots of stars, 200 billion, 100 to 200 billion. It's the last estimate I know. The absolute correct number isn't known, but we know many of the stars by now. And yeah, all of these stars have to be formed. We have a pretty good understanding by now how stars are formed. For example, in this constellation, Orion, that is now coming up as winter is nearing, northern winter, your southern summer is nearing. You will be seeing this too. And of course, in this constellation, you have this wonderful nebula, the Orion Nebula, Messier 42, that is a site of active star formation, one of the nearest sites of active star formation. So that is pretty clear that we need gas, molecular gas, to form stars. There is some discussion on how many small stars and big stars are grown out of a chunk of molecular gas, but we do know in principle how stars form. The other question then is, how do actually planets form? And this has been much more of a debate, and I would say it's still a debate in the recent years, because it's much harder to observe. You cannot observe the forming planets themselves because they are enshrined in lots of dust and gas, so you cannot really see them directly. A big breakthrough there was more than 10 years ago when ALMA, the big sub-millimeter observatory, so an array of 60 or so telescopes or antennas, one might say, that observes in the sub-millimeter, so microwaves essentially. With this big array in the Chilean Atacama Desert, astronomers managed to resolve the regions of planet formation around young stars. And they essentially confirmed what people had expected already since many years, namely that planets are forming in the disks that are surrounding these young stars, these dusty gaseous disks. And the forming planets, or the sites where the planets form, leave black traces in this image. So for example, here is the birthplace of a planet. The planet is accumulating material from this disk, and therefore you have less of the material left, but on the other hand, you get the planet out. So perhaps a good deal. Yeah, there's probably more planets being formed here in this image. And this is also nothing special. So these disks where planets form are now pretty known as being pretty ubiquitous in many, actually most young star systems. We see these disks and know that this is the way, or probably the predominant way, how planets can be observed, or how planets form in young stars. One interesting side aspect is that in order to form a star, you need to compress, so to say, or condense a big chunk, a big cloud of molecular gas into a very, very tiny, compared to the big gas cloud that it is in the beginning, to a tiny sun, a tiny star. And that to do that, you need to get rid of angular momentum, a lot of rotation, so to say, that's in the system. And planets may be the mechanism that nature found to actually get rid of this angular momentum, because planets in our solar system, for example, store, I think, 99% of the angular momentum, while of course most of the mass is in the star, in our case, the sun. So in order to separate, so to say, mass and angular momentum in the forming young stellar system, you need this mechanism of having some angular momentum carriers that surround the star, and these are the planets. So some say that planet formation is a necessary prerequisite in order to form a star in the first place. So it may not be something special or something lucky that a planet forms, but it may be necessary to form a star to actually have planets. And indeed, statistical studies of planet formation or exoplanets in the Milky Way have shown that on average, every star probably hosts at least one exoplanet, one planet. To date, we know about 5,500 planets, so to say, by name. We have actually discovered them. Get to that in a second. And as I said, there's probably, or very certainly, many, many more around stars that we just haven't observed yet. As I said before, there's 200 billion stars in the Milky Way alone. And of course, that's just one galaxy out of many. There's other galaxies. This jewel here, not quite sure if you can see it from Brazil. It's the Andromeda galaxy. Yeah. But of course, there's plenty of other galaxies that can be seen in the south. And in general, there's just a huge wealth of galaxies, from extrapolating the numbers that are observed in very, very deep observations, like the Hubble Deep Field, or in this case here, the James Webb Deep Field. If you extrapolate the number of galaxies from the early universe until today in these tiny fields that telescopes observe very deeply to the entire observable universe, you get a number that is interestingly similar then to the number of stars in our galaxy, namely 200 billion. That's also roughly the number of galaxies that probably exist in the visible universe. So 200 billion galaxies, not all of them 200 billion stars, but all of them probably billions of stars, and most of them probably at least one planet. Well, you can do the math. There's a lot of planets in the universe. Okay, how do we know about specific planets? We do observe that there's different techniques. The most successful technique so far, with which most of the planets have been observed, is the so-called transit method, where very simply, I hope you can see the animation, you do look at a star and just measure its brightness, its photometry over time. And let me see if I can play this once more. And as the planet moves in front of the disk of the star, it covers a tiny fraction of, or blocks a tiny fraction of the light of the star. And this can be observed with modern cameras. You can observe this from the ground, and then you have to take into account atmospheric variations, or you can do it from space. The Kepler space probe is perhaps well known, that has observed most or discovered most of the exoplanets that we know. This is an example of how you can do it from the ground. You actually don't need a very big telescope for this. This is the TRAPPIST telescope, operated by various Belgian universities, and named not just after the monks, the Trappist monks, but also after the beer that they brew, because these astronomers apparently are fond of that beer. And they were quite lucky. The first exoplanet system that they discovered already had 7 exoplanets in their system, so TRAPPIST-1. And here you can see the actual measured data, where you see the dip in light is not very large, and this is already a pretty extreme system where the dip is relatively large. So here you have roughly 1% or 0.5% of dimming as the planet moves in front of the star. There's other systems, and so this is the case because the planets are roughly as large as Earth in this system, in this TRAPPIST-1 system, but the star in this system is only about as large as Jupiter. So this is a dwarf star being surrounded by 7 roughly Earth-like planets, and therefore the contrast, so to say, the contrast change is quite extreme. Now, if you're looking for Earth-like planets around Sun-like stars, then the dip is much smaller and better observed from space, where you don't have atmospheric fluctuations. But in order to make specific observations, so for example, to measure at extremely high angular resolution or at extremely high point source sensitivities, you do need to do this from the ground, and therefore the next generation of optical telescopes all of them have as one of their main science cases the observation of exoplanets. The extremely large telescope that is currently being built in Chile is no exception here. Also, exoplanet science is one of their prime science cases. The ELT is going to be the largest optical telescope in the world, 42 originally, now 39 meters of diameter. That's the size of the mirror. That's composed of 798 segments. Each of them are 1.5 meters or so tall, and they need to be adjusted to each other with micrometer precision. So that's quite a technical feat. And the telescope is really gigantic. Anyone of you who ever has observed with or near an 8-meter telescope, one of the current largest telescopes that we have, you may be impressed by this image. Made by Roberto Tamay, the project manager the project manager for the ELT. This shows an VLT class telescope on the Nasmyth platform, so where just the cameras will be for the ELT to size. Right? This is to scale. So if you stand next to one of these 8-meter telescopes, they look gigantic, but in contrast or in comparison with the ELT, they will be toys. It's really quite a step, quite a leap to go to the ELT. And it's becoming real. This image has been released a couple of weeks ago by ESO when they completed the construction of the dome. So this is taken from Paranal, where the VLT is, towards Cerro Armazones, where ELT is currently being constructed. And the construction is half finished. The first light is planned for 2028. So we'll see. Okay, what does this have to do with exoplanets? So coming back to the science, these are the 3 cameras that are currently being planned for the ELT. I will only highlight one here that's to the right in the orange box. That camera is called METIS, and I used to work for that instrument or for that collaboration for 5 years as Anna said in the beginning, as their calibration scientist. Just a little technical intermezzo here for those who are interested in instruments and techniques. This is how this instrument will look like. The instrument is huge. It has a total weight of about 21 tons, and just the calibration unit, which you see in pink on top of it, that allows to shine in point sources and specific photometric fluxes and alignment cameras and such. Just this calibration unit alone has roughly the size and the weight of a Fiat Punto. So this is just the calibration unit of one of 3 cameras for the telescope. So this is really just telling you what size that is. And that has, I'm not just saying this to impress you, but this also shows that astronomy has become, it's no longer, so to say, an innocent small thing that you do from your backyard. It's an industry, right? And we will get to this when we talk about the carbon footprint, which also has to be taken into account appropriately. All right, so the science that METIS is after, many things. I mean, I was mostly actually involved in the active galactic nucleus science because that was my research field, but the exoplanets are also quite fascinating. The exoplanets science that METIS wants to do, the one image, the many million euro image that METIS is after, I can already show you, although the instrument hasn't yet been built. Of course, it's just a simulation, but you have to believe that this is what we will see. So the idea or the hope is to see an image like that. And this will be an image taken in the thermal infrared, so at 10 micrometers, where you're sensitive to temperatures of about 300 degree Kelvin or 27 or so degree, 23 degree Celsius. 300 Kelvin, 23 degrees Celsius. So roughly room temperature, perhaps not in Brazil, but at least here. And this shows you a possible view onto the nearest stellar system to Earth, the Alpha Centauri system, which, as you may know, consists of 3 stars by itself, Alpha Centauri A, B, and Proxima Centauri. And if, and this is not yet known, but if Alpha Centauri A, the largest star, has planets, which very likely it will have, then this is how they will look like. So the first spot, the left spot, so to say, is excuse me, is an Earth-sized planet that's at half the distance to the star than we are to our sun. So half an AU, half an astronomical unit, about 75 million kilometers away from the star. And the second one is a planet that would be Earth-sized and Earth distance to the star. And the star is also not too different to our sun. So, and this is an image that you would get after roughly 5 hours of integration time. You don't want to know what that costs at the ELT, but that will be taking this image. And that image would be quite fascinating and quite dramatic, right? It would show an Earth-like planet in our very nearby neighborhood. Yeah, that's also the reason why this is done from the ground and in the mid-infrared, because only in the mid-infrared you can observe Earth-like planets that are whose surface temperature has is about 300 Kelvin. Right? Okay, so we do know by now 5,500 exoplanets. We will know in the next coming few years many more planets, and probably several Earth-like planets. We will probably be able to observe them directly. You know, this is not just, I mean, this image is nice, right? But it's not just this image. What you can do, of course, if you resolve the light from the planet, physically resolve it, or in spatial resolution from the star, you can, of course, take that light and put it through a spectrograph, which obviously is planned to do in METIS and with the ELT as well. And then you can analyze the atmosphere, and you can get an impression of what is actually happening on this planet. Does it have an atmosphere? Does it have an ocean? Does it possibly have life? And there's these well sought after biosignatures. Does it have any imbalances that we cannot explain with natural processes alone, for example? So the next question that comes, and that's of course a very hard question to answer, is there life somewhere else? And to get to that question, I would like to ask the question whether Earth is special. So do we expect to see lots and lots of Earths everywhere? Are there planets B, one could also say? And to get to that question, I'd just like to remind you of a few factors that do make Earth special. So one factor is that obviously planets need to be in the right distance from the star, the so-called Goldilocks zone or habitable zone, where we have liquid water on the surface. This is by no means an absolute requirement, so to say, but it's the only thing that we can imagine at the moment, because we don't know we cannot imagine life without liquid water. This is just because that's the only life forms that we know on planet. All are based on, or do need liquid water in one form or another, except for perhaps some weird microbia or so, but I think also they were born in water at least. So that seems to be a prerequisite, and that already narrows down the number of planets quite substantially, because many planets that we know, including in our solar system, are outside this habitable zone. Another factor that seems to be very important are magnetic fields to shield the planet from cosmic radiation. Cosmic radiation are fast particles. In our case, they come mostly from the sun, but they could also be from a nearby supernova, or if you're living in an active galaxy, they could be coming from a jet or some other phenomenon in the galaxy. And probably it doesn't help the evolution of complex, intelligent life, with millions, billions of years of evolutionary cycles where the genetic material has to evolve and evolve and evolve. And it probably doesn't help if all life gets fried every 100 million years or so. Then this whole process has to start over and over again. So that will probably be a killer for any complex, intelligent life. Another thing that is quite special about Earth is that it has, so to say, a built-in thermometer. And that is because Earth has active plate tectonics. There's a cycle called the carbonate-silicate cycle that essentially works in a way that volcanism releases CO2 and therefore produces global warming, natural global warming. That's been happening over hundreds of millions of years, billions of years, even since the beginning of Earth. This extra warming leads to more erosion. So the rocks bind CO2, and then since there's fewer CO2 in the air due to that process, Earth gets cooler a little bit. This leads to less erosion. Then you have again more CO2 from the volcano, and the whole thing starts over again. So you have some sort of control loop built in. If you have too much CO2, you have more weathering of the stones, CO2 gets removed. If you have too little CO2, you get the volcanoes that regularly erupt, and they add some CO2 to the Earth's atmosphere. So that has helped in the past to stabilize Earth, both from having a too hot climate and from totally freezing over. Both of these situations, according to climate, to paleoclimatic archives, have nearly happened in the Earth past, but they haven't fully taken over. So Earth has been habitable for life, or has been seeded with life since a long time, apparently also due to that mechanism. And then, of course, Earth has a very, very big moon compared to the size of the planet that helps to stabilize the spin of the Earth, and probably that also helps to foster complex life. If you have regular day and night zones and regular seasons, and things are not totally turning up and down, you have regular crop yields. You can do farming, and all these things are helped by having a moon that stabilizes the rotations. And then we have a giant planet in our solar system that takes various hits for us. For example, here the comet Shoemaker-Levy. Had that been flying around in the ecliptic plane for much longer, it might have hit Earth, and that again might have produced or might have been an event of mass extinction. And then again, you can start from anew with building your complex life. So it also helps to have a giant planet. And then last but not least, we have a pretty boring sun that also helps. So even compared to other suns of G2V type, so the spectral type of our sun is very predictable. It has this 11 or 22-year cycle of sunspots, which is actually just starting again now. So if you have sun protection glasses, do look up and do look into the sun, but only with these protection glasses, and search for some sunspots. They start appearing again. But apart from that, our sun has been constant or nearly constant without much changes over a very, very long time. All right, so from that compilation, you may already see that there is many factors that do make Earth special, and it's not at all clear that any other planet that we do find would have the same set of parameters that make it so suited for complex life. One warning here, since I'm talking about the sun and the climate, I would just like to show this graph from the latest IPCC report, the International Panel on Climate Change by the United Nations. Just to clearly say and show here, because that is sometimes confused, we can, or climate scientists these days can simulate both the natural behavior that our climate would be following if there was just solar and volcanic inputs. You can see this on the right-hand side as the green bar, or the green line, and the impacts of this natural behavior and the human added contributions, that is the various greenhouse gas emissions on top of it. And you can see very clearly that for the last 170 years or so, there have been variations in the natural drivers of our climate. There have been volcano eruptions. The sun isn't always the same, not exactly at least, but this would not have led to a significant warming of our planet. And really the only explanation that climate scientists have for that is the observed increase in greenhouse gas emissions. All right, so then does that then mean that there is no planet B, or is there a planet B? If we look at all these parameters, the billions of exoplanets, and possibly with some special parameters. Well, we should ask, what does it mean to have a planet B? I mean, with so many billions of stars in the universe and alone in the Milky Way already, I think it's probably pretty likely that there will be a planet that is very similar to Earth in many of the parameters, including having a big planet that protects us from asteroids, and having a moon that stabilizes our spin, and having a silent sun, and being in the outskirts of the galaxy, and what not might be added as a requirement. There probably will be several planets that do fulfill these requirements. But then the question is, would that be planet B? Well, probably still not, because we cannot get there. We can't even get to Mars. I mean, there are these plans to settle on Mars. I find them extremely fascinating. I like to read science fiction books about these things. That's really amazing, but it's not a solution to solving the problems that we have on our planet, because we could never move 8 billion people there, right? If we wanted to go to faraway exoplanets, then the situation is even more difficult. This is now the slide perhaps most interesting for the non-astronomers or the astronomy youngsters in the audience. Just a little question about the distances in the universe, in case you haven't visualized this yourself. So if you take the sun with a radius of about a diameter of about 1.3 million kilometers, and let's shrink it to the size of a marble, then you can ask the question, how far away would the next star be? And I adjusted it for Sao Paulo, for Porto Alegre. So if the sun was just a tiny marble, how far away would the next sun be? Well, you can probably guess the answer. It's actually in Sao Paulo, so about 500 kilometers or so away is the distance. And take a moment to visualize this for yourself. If the sun is a tiny marble 500 kilometers away, there would be the next tiny marble with even tinier planets. So that already tells you the universe is mostly just empty, and that's an important message and realization to learn in this discussion about, is there a planet B? And then finally, if there was a planet that was like Earth and it was accessible, or we could get there, perhaps there's already people there, and they might not like us. So, okay, so we better protect our own planet. And that brings me to I guess the third part of the talk about the urgency of the climate crisis. I don't want to talk in too much detail about the basics, because I'm pretty sure you're aware of this, but I would like to show you this graph that highlights the urgency of the situation in a very impressive way, in my view. This is from the Global Carbon Project. This is the latest movie that they have, but it's already 3 years old. You can imagine how it would look like today. And it's a movie. I will play it in a second. It shows a bucket, and this bucket represents the amount of greenhouse gases, let's say CO2, that our atmosphere can hold in order to warm up by 1.5 degrees Celsius compared to the pre-industrial age, so 1850 or so, compared to today. And there is a conversion involved between CO2 concentration and atmospheric warming. That's called the carbon sensitivity of the Earth. That's pretty well known these days. There are uncertainties, as with any scientific model, but we know roughly how much CO2 can be added in order for Earth to warm up by 1.5 degrees. And we can look then, how far are we? How near are we at these 1.5 degrees? And what is the historical evolution? So now let me play this movie, and you can see the bucket is filling from the end of the 19th century. Mostly Europeans are adding to this, and the USA, and the rest of the world is not contributing that much these days. And then you can see later on China is becoming a major emitter as well. And now, of course, China is the most significant emitter. The bucket is filling faster and faster. Let me just play it one more time. Because what's impressive for me here is how it begins very slowly and how it's accelerating towards today, essentially. So now it's starting to accelerate, and it's becoming faster and faster. And in 2020, it looks like, there isn't much left. And of course, that is exactly the message that is being sent by climate scientists, by the United Nations, and to some small degree also by Astronomers for Planet Earth, all the time, that there is really not much time that we have left. Okay, so that's the bad news, so to say. Is there also good news? And yes, there is, definitely. It comes from the same group here, the Climate Action Tracker. They take stock of all the policies that are in place and what would be needed to get us to this 1.5 degree goal. By the way, 1.5 degree goal, in order, this has been defined in the 2015 Paris Agreement, because we think that at 1.5 degree warming, the Earth will still be mostly like it was before, and more importantly, the whole global warming process would be reversible. So if we have only 1.5 degree warming, and we're very close to that point, then if we stop emitting CO2, all would slowly normalize, and over the next decades and centuries, things would go back to normal. That's the good news, right? At 2 degrees, that might still be the case, but we're not so sure about that. So that's why everyone says, okay, we should really limit it to 1.5 degrees. Now, where are we at the moment? What is, if everything goes just business as usual, where would we end up at the end of this century, in the year 2100? Well, not too long ago, 5-10 years ago, we would have ended up in the black part of this thermometer at 4.5 degrees warming. That was the most realistic scenario if things would just continue to go business as usual. Now we are in a much better situation. If everything works as, in the most ideal case, we would be in 1.8 degree. However, oh, sorry, this is in German. I'll translate it. So the most optimistic scenario is 1.8 degree. The promises and the goals that countries have made would lead us to 2 degrees. So for example, in the European Union, we have this Fit for 55 package, meaning 55% emission reduction until 2030 compared to 2008. That would lead to a 2 degree world if all the countries who promise these things would actually do that. However, if you then look only at the nearby targets, the targets until 2030, then it would lead us to 2.4 degrees. And if you only look at what has actually been implemented in law, and there is a huge difference, as I know a little bit, at least from working 1 year in this policy advocation agency, there's a huge difference in the goal that you set, which doesn't cost anything, and an actual law that you make. And the actual laws would lead us to a 2.7 degrees warmer world. And that is still a massive problem, because 2.7 degrees is not just above 1.5 degrees and above 2 degrees, it's a lot above 2 degrees. And every 0.1 degree matters hugely and makes a huge difference whether parts of the world, thinking mostly about India here, but also Africa, and probably not quite sure about the climate impacts it would have directly on Brazil, but many parts that already have relatively warm climates would see massive problems at a 2.7 degree warmer world. This is, just to show this in a different scenario, this shows you what we would need, the green bar, this really very quick reduction of emissions, and the blue band is what is actually in place at the moment. So yes, there is the ambition to stop emissions. Emissions have been slowing down. That's the good news. Emissions might have peaked this year or will peak next year. That's not totally sure, but that is also probably good news. But they're not declining fast enough. People are transitioning. There's lots of renewable energy being built, and electric cars are being used, and etc. But it's not happening fast enough. And the fast enough is a very important part. It's this so-called ambition gap. So we need to work on this halving of emissions roughly in the next couple of years in order to still have a chance to reach 1.5 degree goals. All right. So that brings me to the almost last part of this talk. And that's now back to the astronomy question. Now we have covered astronomy and the climate crisis. Now, what do these two have to do with each other? What is the link between galaxies and exoplanets and climate on our Earth? Well, first and for all, of course, astronomers are members of this planet as well. They are citizens. They can make their voice heard. But also astronomy, as I said before, has become an industry and actually has a quite significant carbon footprint on this planet. Within this organization, Astronomers for Planet Earth, several of us did so-called carbon footprint analyses on various activities. So here, for example, with a colleague in the Netherlands, I looked at the carbon footprint of all astronomy research in the Netherlands. That were the numbers for 2019. There was the the ones, well, before the Corona pandemic, so we took that year. And you can see here that the average emissions, this is now for the average institute, are about 4.9 kiloton CO2, and it comes from a variety, or we looked into a couple of sources. Flying, in our case, is the largest source of emissions. Electricity, the next one. This is the electricity part is shrinking quickly as we install more renewable energy. Heating is also decreasing. Commuting is not decreasing fast enough, but a little bit. And supercomputing, as it's also based on electricity, is also decreasing. But the flying part, we don't really know how to decrease yet. So that's one big challenge to overcome. I mean, obviously, we can give seminars all across the world using online technology. That's great. But of course, we do want to fly eventually, at least to, or occasionally, let's say, to actually meet people in person. And I would also not advocate to stop flying altogether, but to be more considerate about which flight is really needed and perhaps extend your stay and, you know, make it really worthwhile. Another part is if you look at the carbon footprint of a big observatory, for example, here, ESO, this is the European Southern Observatory that's operating these big telescopes, or some of the big telescopes in Chile. They have a quite different carbon footprint constitution here. For them, energy is the largest share, so it's not flights, but it's energy. And then the second biggest point is purchases. So this is if you look also into the whole downstream chain of emissions. If you buy a computer, what does that mean? Well, someone needs to construct the computer, and that uses energy as well. So if you look into all that chain, you get a large contribution for purchases in order to build the instruments and the telescopes. And business travel in their case is only 10% because they operate these big telescopes, and that's the dominant factor. And then other includes things like commuting, but also food and heating and other things. Okay, and then last example here, the construction of a big telescope. This has also been looked at for the example of the ELT. Here we have another challenge that is also not yet really overcome. In this case, it's the materials itself that have a large carbon footprint. So for the ELT, which is a steel structure surrounded by a concrete structure, or the other way around, no, this way around, and of course has lots and lots of installations. The steel part is making the largest part of this 63.7 kilotons emission budget. And steel, as you may know, it's not just energy intensive to produce steel, but you actually need to, or at the moment at least, steel is produced in a way that you use iron oxide. And in order to make this iron oxide into steel, you need to add coal, not just for the heat, but actually to use the carbon atoms, the oxygen atoms, and build them into the steel so that it actually makes the material. And in that process, the carbon atoms are burnt and released as CO2. There are different ways of making steel, so-called green steel, using direct reduction and hydrogen and so on, but this is not yet available in large quantities. So for steel, and similarly also for concrete, where the production of the constituents that you need to produce concrete also release CO2 in the process of making it. So these are things where you cannot easily just switch to green energy. This requires a little bit more thinking how to make them really green. And then, of course, there's 2% explosives. I guess they will remain as long as we explode mountains to build telescopes. All right, so how can this be overcome? Given the time, I think I'll swap over this plot quickly and just go to the summary of this plot that we made for the European Astronomical Society meeting. We compared the 2019 and 2020 meeting at the time to look into the flight emissions, how they can be overcome. And we found that obviously most, or not obviously perhaps, but most of the flight emissions come from actually just a few participants. 10% of the participants were responsible for 50% of the emissions. And these are obviously the ones that fly larger distances. So the domestic flights are taken by many more people, but don't have as much emissions. And the big number that perhaps is interesting to keep in mind is for this particular meeting, which is the largest astronomy meeting in Europe, over 1,000 participants. The difference between the in-person meeting in 2019 in France and the online meeting due to the pandemic 2020 was a factor of 3,000 in emissions. So by moving an entire meeting to the online format, you can save a factor of 3,000 in emissions. That's quite something, I would say. And many people actually say that the online meeting was more enjoyable, for this particular big meeting, because it's much easier to switch between sessions and to actually talk to people you really want to talk to, and not just bump into some random person, so to say. But yeah, so I think there would be good reasons to move at least these big meetings to online meetings, and reserve the flights for the smaller workshop type meetings that are actually needed. All right, let me go over this given the time, and just end with the slides of what else astronomy can do. Of course, we can look into our own carbon footprint. We think this is important because you need to be aware of what you're doing yourself, and make yourself better before telling someone else what to do. So what can astronomers do in addition? We can communicate, of course, to the public, and many astronomers love to do that, and many are really good at doing this. And everyone in the world, mostly everyone at least, is really interested in astronomy, right? That's great. There's lots of amateur astronomers, there's lots of enthusiasts who would like to know about exoplanets and black holes and the early universe. So astronomers have a huge audience and can use that audience to convey science, the scientific method, and then, show a slide from time to time that, for example, like here, shows the difference between the solar irradiation on Earth, the yellow curve here, and the temperature on Earth, which some people who want to say that it's just the sun being crazy, they only show it up until about 1960, and they say, look, this follows each other. Well, if you look at the entire timeline, you see that after 1960, the sun has become a little bit less active again, but the temperature on Earth has still been rising. So it's one thing to convey this scientific method. But we think at Astronomers for Planet Earth that the most important thing that we can contribute as astronomers is this perspective of looking on Earth from the outside, from space, and conveying this almost feeling a little bit, although it's very hard to have a feeling for billions of kilometers of space, but at least give this feeling of, how thin is this atmosphere actually? Show an image like this. This is showing the Netherlands here, where you see the Earth appears huge, but of course it's very tiny compared to the rest of the galaxy. And on Earth, you have this tiny, tiny sheet of about 8 kilometers of atmosphere that's separating all life that we know from nothingness and from dead space so far. But then, of course, you can look from further away. You can look from the moon and show an image like this one, which is a really well-known and I think quite fascinating image. It was taken by the astronauts on Apollo 8 as they didn't land on the moon, of course, yet with Apollo 8. They just rotated around the moon a couple of times and then went back to Earth. And when they came around, I think the first time, they saw the moon rising, the Earth rising on the moon. So the image is actually rotated 90 degrees. But anyway, there's a YouTube snippet of the audio that the astronauts at the time made, and they were totally excited by that and said, give me the color film, let's take this image. So it's really impressive to see that, and they must have been totally in awe at seeing Earth in the middle of nothing here. And of course, what that all tells us, and this is the last picture that I want to show in this context, is this huge perspective that astronomers can give. And you may know this image, which I think is the best one to show how small and how isolated somehow Earth is, and how special Earth is perhaps to us, is this picture called Pale Blue Dot that has been taken by the Voyager 1 space mission that has observed or visited various planets of the outer solar system. And when it was done with its mission, it was commanded to turn around, which was tricky because the antennas to communicate with Earth were on the backside of the space probe, and when they turned it around, the antennas were looking into deep space, so they couldn't command it anymore. But nevertheless, it took this image and fortunately turned around again, looked into the inner solar system. It saw these stripes of reflected sunlight, and it saw this tiny spot, and this is us, right? This is our planet, a quarter of a pixel. And Carl Sagan, the astronomer behind making this picture, wrote a book about this. And I'd just like to read one sentence from this book, where Carl Sagan wrote, to me, this image underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. I think this is a quite nice view and perspective that astronomers can, and I think should, convey to the broader public, to let know that this is really, that we can really be quite lucky to have that planet. All right, let me move on here to the last two slides, given the time. So last but not least, 3 slides or 4 on the organization that a couple of astronomers have founded in order to A, measure the carbon footprint of astronomy and try to bring it down. There is some progress on that as well. And B, convey this special perspective, this pale blue dot perspective, you know, that we're isolated in space somehow, and, you know, not take away any scientific or science fiction visions. I mean, that it's great to have vision, and it's great to explore space and, you know, do space flight, and I love all these things as well, but make clear that there's a difference between this exploration research part, also looking into other exoplanets, and what we have on Earth, and there's really just no alternative than protecting our planet, obviously. All right, so Astronomers for Planet Earth, this organization where we're looking into our own carbon footprint and doing outreach on this astronomical perspective, has been now about 2,000 members from many countries around the world. And we have these goals of sharing this astronomical perspective, as already said, but also explaining the science behind climate change. This is especially important in the US, where science of climate change is very politically loaded, let's say, and astronomers are often seen as neutral parties that are not taking part in this political discussion of, hey, you know, is climate science good or bad, but they are doing something else. Yeah. And so they can kind of argue from the neutral ground and say, look, you know, we know a little bit about planet atmospheres. You know, if you're an exoplanet researcher, you know that as well. Or we know a little bit about radiation budgets, or about temperature, or about climate models or something, and just explain what they mean and try to convey this to the public. All right, and then we have established a community, partly through workshops that we've organized, for example, at the European Astronomical Society, but also at the AAS meeting. There was such a meeting as well at the SOCIAS, the Chilean Astronomical Society meeting, and various other astronomical societies. AFAS, the African Astronomical Society, recently had their first sustainability workshop, and we try to help and support and speak if we can help with that, or organize or suggest speakers to that. I'm not actually sure if this has happened at the Brazilian Astronomical Society meeting yet, but perhaps it's something that you would like to think about. We have produced a number of articles, for example, here, a special issue in Nature Astronomy in September 2020, where we produced a number of papers analyzing the carbon footprint, but also looking into what does climate change actually mean on astronomical observations. You know, if the climate is warming up, we get more seeing, we get less stable conditions. That changes the way we can actually observe from the ground. All right, so this was a very short bit now about Astronomers for Planet Earth. Time is up, and I don't want to keep you too much waiting. So we have a quite fancy website produced by a design company for us about a year ago, astronomersforplanet.earth, and I would like to invite you all to visit that website. And if you want, join the community. You can click on this little join us button, which leads you to a form. It may take a day or two until it gets answered, and then you can join our Slack space and discuss with us about a number of different topics, whatever you find interesting, be it carbon projects, it could be planetarium shows or books or conferences or other projects that you would like to do with us. We would be very happy to have you. We do have a newsletter that appears a few times per year to keep you to give you an overview of everything that's happening. And we have various sorts of meetings. A webinar is currently being planned to be held again. So there's a community there that can help you discuss any of these matters if you're interested. All right, that's it from my side. The one message that you should keep in mind, in case you want to keep one big message in mind, that is, there really is no planet B. There is some astronomical significance to that. So let us protect planet A together. Obrigado por sua atenção. Thank you.
Thank you. Thank you very much, Leo, for this wonderful seminar. Now, questions from the audience? Basilio and students, think about it.
Should students?
Not yet,
No students yet.
but think about that.
Okay, thanks, Leo, for your presentation. I hope you can hear me well. I'm worried about I appreciate what astronomers for planet Earth are trying to do, but I do worry about the neutral attitude. I'm pretty sure you're probably aware about that, for instance, a single billionaire on the planet, regardless of where he or she lives, by flying his private jets all over the planet, by having huge properties or gadgets that consume extremely large amounts of energy, a single billionaire leaves a carbon footprint that is probably similar to that of hundreds of millions of poor people on the planet. I don't think we'll manage this situation to our planet A home, which is a common home to everyone, if we don't tackle this social inequality issue on a worldwide basis. That's one example about how neutrality may not be the best attitude, depending on what you mean by neutrality. A second example is, okay, astronomers are caring about the carbon footprint that their observatories and institutes leave. So do you guys encourage armed forces and defense industries in different countries like the US, China, Russia, and NATO to do the same, to estimate the carbon footprint that they leave?
Okay, well, thanks for these comments. These are very tough comments or questions to answer. Let me try to tackle them. So regarding the carbon footprint of billionaires and generally rich people, you are, of course, absolutely right. I mean, there is a huge inequality. The richest, I think it's the richest 1% has a carbon footprint that is equal or even larger to that of the poorest 50%. That's one of these numbers that is frequently shown, right? So there is, you're totally right. There's this huge inequality, but we have to keep in mind that astronomers, at least in rich countries, are part, perhaps not of the 1%, but part of the 2, 3, 4, 5%. And they're also responsible for a much larger carbon footprint than most of the rest of the world. So I think it's the problem with this with solving climate change is that there's so many people who are responsible for it. And so everyone can say, I'm not the largest offender. This person's doing more, right? And for example, in Germany, there's always the discussion, Germany has a carbon footprint, a share of carbon footprint worldwide of about 2%. So some right-wing parties in Germany say, we're only 2% of the world. I mean, why should we care, really? I mean, there's so much bigger emitters like China, so why should we care? But then, if you look at all the emitters in the world, there's 5 emitters, 5 countries that emit more than Germany. Yes, it's China. Yes, it's the US, a couple of others, but then comes already Germany. So, even 2% is a huge contribution. And of course, astronomy is much less than 2%. You could say it's negligible. Yeah? But I think the important point that we want to make is not the total amount of emissions compared to others, but it's the moral obligation that these are our emissions. These are the emissions that we have under control, where we can say, okay, do we really want to have this conference on Hawaii? And what signal are we sending by flying 1,000 people to Hawaii? Or could we perhaps have this meeting in multiple spots so people can take a train and the rest can connect online? This would just be a very strong signal that we're sending in a world where people say, the scientists, they talk all the time and then I don't care, I just do my thing. If they see, look, astronomers who know about there is no planet B, care about planet A, and they realize so much and they're so afraid of climate change that they're changing their own ways, that would be a very, very strong signal that would go way beyond the few kilograms or tons of CO2 that we would save. So that's I think the point to make here. And the other part about observatories, yeah, I guess it's already included in that, right? Yes, I mean, observatories do have, I'm actually not quite sure. Can you repeat the second question?
I was asking if astronomers for planet Earth encourage defense industries and armed forces from different countries to make this estimate of carbon footprint that they see. It would be, interesting to know.
I mean, the defense industry, or generally just waging war, is of course bad in so many dimensions. I would put the direct human dimension first here before even talking about climate change. But I mean, yes, of course, we should avoid war at all costs, I would say, if at all possible. And that includes then the whole defense industry. We don't have a specific call on the defense industry yet to say, look, you should do your carbon budgets. One should say that the defense industry is not even part of international climate negotiations, right? You have these various sectors that every sector is treated differently. You have this energy sector that is pretty much under control now. We know how much emissions we produce from, let's say, burning coal and things. There's the ground transport that is also pretty well known, how much comes from cars. There's heating that's well known. There's land use and land use change in forestry, this LULUCF factor that's well known. International aviation is not regulated and military are not regulated. And of course, the reason is because there's too strong national interests to do that. But yeah, I mean, that is a huge problem. I think at the moment they're hiding behind the fact that they're also only 2 or 3% of the global emissions, according to estimates. So, which is of course crazy, right? It's like a relatively big country, European big country like Germany. All the military is producing as much emissions as 80 million people, 80 million rich people. So that is dramatic. But my hope would be that as soon as the rest of the emissions go down, the pressure on the military will be higher to change their ways too. But yeah, I mean, this is, of course, the most difficult question at all. And I think the point that I would like to leave here is we should not wait until someone has solved their problem entirely before we get active. Right? It's a question, a problem that we have dragged our feet upon, not doing things about this for way too long. Thinking back of, Rio de Janeiro summit in the 90s, people have not acted on the warnings of climate scientists for decades, even centuries almost. And so now we cannot wait anymore and say, oh, we need to wait until China has fixed their problem. No, we all need to do whatever we can. And even if it's just 0.001%, just to do what you can.
I'll get my electric car, don't worry.
Or use a bike.
Questions from the students? You can ask in Portuguese and then we translate if you have any questions from YouTube and from Zoom. Kepler?
Yeah, first, I agree totally with Leonard that everybody has to give an example, even if it's tiny, it's more than complaining about the major polluters. But my first question is, what is the real effect? I don't think like when you show the declines of the carbon emission, I don't think it is realistic to assume that it's going to go to the optimistic view. So I think, what is like you said, 2.7 degrees if we keep like it is? Is that correct?
Yes, that's the current best estimate by a group called Climate Action Tracker.
Okay.
Their next update is out in a couple of days. So they do this at every COP. The one that I
Okay.
showed is from last year's
Yeah.
COP. So the next estimate should be out in a couple of days. I don't think it will have changed a lot, perhaps by 0.1 degrees or so, because last year already included some of the emergency measures from after the Ukraine war started. So that did change things from the energy and climate side. The war itself is, of course, terrible, but from the energy and climate side, that did improve things. Because Germany, for example, realized, and all of Europe realized, that buying cheap gas from Russia is perhaps not the best idea anymore. And so they started to invest in renewables massively. So that I would expect this to increase or to decrease again a little bit. There's at the COP that's starting tomorrow, there will probably be an agreement to speed up the distribution of renewables. The idea is to have a factor 3 expansion until 2030. I think that's actually realistic to achieve. The more difficult problem is to actually phase out fossil fuels. So the expansion of renewables, that works quite well, but actually stopping fossil fuels, not just existing ones, but also just stopping any new projects and not invest anymore in exploration of gas and oil fields, and just stopping working on that topic. That is not working yet, and there's also no consensus inside, because the big oil producing companies prefer not to say we want to stop burning fossil fuels, but they want to have this backdoor of, oh no, we still want to burn it, but then we want to somehow magically separate the CO2 from the exhaust and store that CO2 somewhere underground.
Yeah.
And if that worked, that of course would be a good idea, perhaps, but it doesn't work. There's no one yet has shown that it works on a massive scale. They can only separate a small part, or a part, let's say, I don't know, 50% at maximum of the emissions. The rest is still in the atmosphere. And then there is no safe way really to store it underground. And it's very expensive. So this is just not a real solution. It's just a way to say we want to keep burning and burning. And that's the big problem now, to stop the fossil fuels.
Not only keep burning, but OPEC is planning an increase of 18 to 30% in the oil production in the next 10 years. So it's not going to reduce. Yeah.
I mean, the good side, again, I'd like to also always share some good views, to not just leave the bad news. The good news really is that renewables are now the cheapest energy source in most places of the world, for most applications. So that is the reason why the renewables are rising so fast, right? Solar power is just so cheap that when you want to install, when you want to have electricity, from most parts of the world, it just makes a lot of economic sense. You don't have to be a green person or eco-minded or whatever. It just makes economic sense to install solar power.
Yeah.
And that's a very important achievement. And now, that's why the expansion of renewables works, right? But the existing fossil fuels are still here.
Yeah, just one more comment is, we have right now in Brazil a drought in the Amazon, the largest ever. And at the same time, lots of rain in the south. So we are seeing the effect. But at the same time, there is always the claim that it's because of El Nino, it's not because of the climate change. So we have to keep pounding on these graphs of the increase of CO in millions of years, right? Not only during the last 100 years, but compared to millions of years. So I think we have to keep pounding that the climate effects are a minor, not the natural climate effects are a very minor compared to the effect of the yield.
Yeah, that's right. And they work on very different timescales, right? That's
exactly. Okay, thanks. Thank you.
So there's a question, João. Go ahead. You're muted.
Hey, can you listen to me, maybe?
Yes.
Oh, okay, perfect. So let me try to just turn my video on so you can see me. Hi, Lau. So I really liked your talk. I just wanted, linking with the comment from Kepler. So do you have any thoughts or opinions, or I don't know, based on the carbon market, which I know that is like a really big discussion now, right? On buying carbon credits or whatever. So is that a good thing, a bad thing in the long term? How do you expect that to evolve?
Depends a bit on what you mean by carbon market. I mean, there are emission markets, in Europe, for example, we have this ETS, the emission trading system, where it's a cap and trade scheme where countries have agreed that the maximum number of, or the maximum amount of emissions in a certain sector, it's always bound by sector. For example, in the energy sector, the total amount of emissions is capped at so and so many million tons per year for the energy sector in Europe. Now, if you want to release CO2 by burning coal and producing electricity, you need to buy a certificate in order to be able to do that. And that certificate, some of them you get for free, some of them you have to get on the market. And the idea is that the number of certificates decreases over time, so it gets more and more expensive to burn CO2. And the other idea is that you will save CO2 in those places where it's cheapest to do that. So for example, if in Germany someone says, I want to still run my coal power plant, but in Spain someone says, okay, I can easily shut it off and turn and build photovoltaic instead because we have enough of sun there, they can turn off their power plant, sell their emission rights to Germany, who's still using coal power plant, and you have the cheapest way of getting rid of emissions. That's the idea. In principle, that could work. There's scientific studies about this, that this is actually a good idea if it's done right, in the sense that the emission, the cap really has to be reduced over time. And you have to take into account all emissions if that is done. That's not perfect yet, but the emissions scheme is not totally wrong. So that is one way to reduce emissions and do it in a relatively cheap way. The other way of thinking about emission certificates or carbon certificates is this kind of volunteered scheme where you say, I take a flight to somewhere, and then, for my good consciousness, I pay 50 euros or $50 or whatever to someone who will plant 5 trees somewhere, and then I'm good. Yeah, that does not work. That simply is that. That does not work for a number of reasons. One very obvious one is if you take a flight now, for example, an intercontinental flight, you release 10 tons of CO2 now. And if you plant 10 trees, they may suck up 10 tons of emissions over 50 years. But what matters is the carbon dioxide concentration we have now. Right now is the peak CO2, and hopefully on Earth. So we need to reduce emissions now and not in 40 or 50 years. And the trees suck up most CO2 when they are big and not when they're young. And in addition, it has been shown that several of these forests that are planted to reduce emissions actually burn down because of climate change, or just don't survive because there's a drought or something else is happening. Someone isn't managing it for longer than a couple of years. So these voluntary carbon reduction schemes are not a good idea.
Yeah, I just said it also because, as Kepler said, the climate situation in Brazil is kind of chaotic now. And I know that, for example, Amazon has some fires there, for example, and tons and tons of carbon that could be trapped right on Earth, let's say, are being given back to the atmosphere. So yeah, I agree with your views in that sense of these double markets. But yeah, thanks for the talk again.
Yeah, thank you. That's indeed very worrisome. And I mean, I'm often also looking at the situation in Brazil and hope that there will be, hope that it will be possible to protect the Amazon forest and the wonderful nature that you have. Yeah.
So I have one question, or maybe two. So in the past, now it's been a year that we don't have a denialist government, but we had that for 4 years, and it was very hard to talk to people, anti-science people. So do you have any advice on how to reach these people to be able to talk about climate change? And is there any statistics if this has gotten better in the world, at least, for instance, in the US, or has gotten worse?
That's that's a very good question too. That actually also comes quite often. Let me show you the one slide that I skipped. It's just one slide that tries to answer that question. So you can look at this organization, this Yale Program on Climate Change Communication, they separate the population, and not just in the US, they do this worldwide, into 6 different groups. They have been doing this since, I think, 10 years or so, and they do this every other year for another country. I'm pretty sure there's also a statistic for Brazil. I'm sorry that I didn't look it up before now, but I can send you the link if you want. So they differentiate between alarmed group, that's those who, who say, oh, it's the climate crisis, we need to do something now. The concerned ones who say, yeah, we should probably be doing something. Cautious, we're saying, yeah, better perhaps do something. Disengaged, they're not interested at all. Doubtful, they say, I don't know, is this really right? Does it really matter? And the dismissive ones are the ones, like Trump, who say China is just playing with us. It doesn't matter. It's not real, and so on. Now the question is, how many people are in each group, right? And the ones you just described are probably the ones in the dismissive or doubtful group. And as scientists, we often want to discuss with these people because we want to convince them of the better argument. But if you look into the numbers of people actually who are in these groups, and this is quite some statistics behind it, you see that this is actually only a small fraction. And that's in the US, where you would think, with all the climate skepticism there. So the message here is that the majority of people, and this is, again, I don't have it for Brazil, but I do know the worldwide summary, and this is true for almost all countries in the world. The majority of people, more than 50%, are typically in the alarmed and concerned, and sometimes also cautious groups. So I'm happy to share a few thoughts just after that of how to possibly reach the dismissive and doubtful ones. But my main message would be, it's not that important to discuss, or it's not the best use of your time, let's say it this way, to try to convince those people who are very, very certain that this is all just nonsense and fake science and doesn't exist. Those people, some of these you will just never reach. There's no argument. You can be a Nobel Prize winning scientist. They would just not listen to you because they're not interested in actual facts. They have their closed worldview and believe perhaps the earth is flat, and I don't know what. There's nothing you can do. The ones in the in-between region, these are the ones who I think are valuable to reach. And if you have a discussion with someone who's in this dismissive or doubtful regime, and you have some people listening who are in the other parts, in the cautious part, for example, then it's very worthwhile discussing, not for the dismissive person, but for the others who are listening to the conversation and who hear that there's actually really good arguments that you can make to say, look, we need to do something now, right? It's not too late and we need to do something now. So that's a reason to discuss with them. And what to say or how to convince. I mean, if you really want to approach these, for example, if they're part of your family, or if there are people you like for other reasons and you want to actually talk with them, I would try with the astronomy view, right? Show them this pale blue dot picture, show them the Earthrise picture, and show them how many planets there are and how special Earth is, and there's no other planet like us, and we cannot get to them. Show us the distances and say, this is really this tiny atmosphere, that's really all we have, and I'm blowing in some CO2 here with my car every day. Can that be really good? Start asking some questions and make them think about what could that possibly mean for us here on Earth.
Good to know these statistics. Gives us hope.
Yeah, but I mean, it gives hope, and I think it should tell us what our strategy for communication is. Namely, not so much try to convince the complete weirdos, but try to activate those who are already concerned. Most of the concerned and alarmed ones are concerned or alarmed, but they're not doing anything about it, right? They sit at home, they read the newspapers, and they think, oh my God, the world is so bad. And then they go on their job. Right? What we need happening is that those people who are already alarmed or concerned go out to the streets, tell their politicians, go on rallies, change the world. Easier said than done, I know, but still, that's the part that we need, that those who already know actually become more active and protest against whatever expansion of fossil fuels and any bad developments.
More questions? I think we're already past time. I just wanted to ask one last question about how is the engagement of Astronomers for Planet Earth in China?
in
The
China?
engagement in China, yeah.
In China. We do have, just looking at the world map again, we do have astronomers in China, but I must say I don't have any personal contacts to astronomers in China, and I don't know of any big group there. I mean, that is difficult, right? With a political system that is, well, not a democracy and near impossible for citizens to raise their voice on problems. It's very hard to convince people there. So we have members, for example, in Pakistan, who want to build actually now a local chapter for A4E. Sorry. We have members in various African states. There's of course people in Brazil, in Chile, in Australia, and most of them are in the US and in Europe. But China is difficult to reach. Yeah.
Yeah, I spent a year there, and it really struck me how people do not talk about climate change in China. And if there's any way we can help with it, because the younger people will care, but they need to, we need to raise awareness.
Yeah.
It's an issue.
Yeah,
Okay.
that's a very, very difficult topic, but yeah, perhaps another seminar.
Okay, and is there, do you have a cohort already in Brazil, or people are just starting to be part? If our students want to be part, they just join, and if they want to be more active, we can organize certain things. In the Brazilian Astronomical Society, for instance, because we didn't have this yet.
I'm afraid okay.
I talk to many things at the same time. If our students would like to be part of Astronomers for Planet Earth, you just join, as you mentioned. And is there any local cohort in Latin America?
Okay. Yes, there is. So by any means, just join. We have these quite easy digital means to get in touch with people. We had a relatively active group in Chile around Yara Jaffe and Carla Ramirez. We have a group in Central America, Breezy in the where exactly is she? I think on one of the Caribbean islands, is active there. We have people in Mexico. I'm again not quite sure who we would have in Brazil, but I'm pretty sure if you did, I mean, we do have members in Brazil, but I don't know all of the 2000s, I'm afraid. If you send a message to our general channel, or we can also have a call in our newsletter, that's all possible at any time, to say, okay, I want to start a Brazilian group, for example, then I'm pretty sure you would get many answers, because we have really a significant fraction from the astronomical community from all the places. So yeah, I mean, by all means, just join. Go to our website, sign up. The most important communication platform really is Slack at the moment. So that's a chat platform with tons and tons of channels. So the challenge there is to search the ones you want to follow and not be overwhelmed by too many discussions and too much information. And we have regular newbie meetups, so where people who are new to A4E can meet some of the older people and discuss how to get involved. And of course, I mean, always also just be happy or just contact me. I'm very happy to be in touch. You have my email address, or feel free, Anna, to give it out to others if they want to join or have any questions, and I can try to forward it to people who are perhaps more local to your place. So, yeah.
Are you done? Okay, Leo, thank you very much. It was really nice to discuss this with you, and yeah, we'll keep in touch.
Yes, gladly. Thanks again for having me, and have a good time. Hope to see you soon again. Okay, bye.